So in this video, we're going to look at another constant coefficient problem, but the third type of solution that we have involves complex roots to our characteristic equation. And so we're just going to go ahead and jump ahead to the characteristic equation rather than go through all the steps. Recall that essentially we're going to substitute or derive from the second derivative. We're going to obtain an r squared. The constant from the second term gets coupled with an r, and then the term by itself that involves no derivatives will just become a constant. And again, you can see how we obtain the characteristic equation by looking at my other constant coefficient videos. So once we obtain our characteristic equation, then we need to be able to find the roots. And there are no factors of 10 which add to 2, and so we're going to need to use our quadratic formula to obtain our roots. So -2 plus or minus the square root of -2 or +2 squared is going to be 4. And then 4, that's just in the equation, times a times c, and then divided by 2 times a. And so we can see that under our radical, 4 times 10 is going to give us -40. 4 minus 40 is going to give us -36. And the square root of -36 is going to be 6i. And our 2 has to divide both terms. And so we end up with -1 plus and minus 3i. Now, the way that we obtain a solution for our differential equation that is real is that we have to apply Euler's formula to convert the complex exponential into a trig function. And so I'm just going to run through this somewhat quickly. So e, and with only one root, because the other one will differ only by a constant. 3ix. And what we're going to do is we're going to split the exponential. X times -1 is going to be -x. And then the other exponential will be 3xi. And we're going to apply Euler's formula to the complex portion, which will then give us cosine 3x plus I sine 3x. Now, e to the -x cosine 3x will then be one solution, and e to the -x sine 3x will then be the other solution. The I can be absorbed into the constants. And the only difference between the positive root and the negative root is that you will get a negative sign in here. So we can ignore this. And so generally speaking, if r is equal to lambda plus mu I, then your solutions are going to be e to the negative lambda, or e to the lambda, cosine mu x, and c2 e to the lambda sine mu x. And so in this particular case, our solution will have lambda equal to -1 so negative x, and mu is equal to 3. Lambda x. Okay, so if these are the solutions, then how can we verify that these are, in fact, linearly independent? We can, there's quite a lot of algebra involved, but we can find the Wronskian. It turns out for this particular example, if you calculate the Wronskian with sine as the function in the first column, you end up with negative 3e to the negative 2x. Again, this negative 2 should match the opposite sign of this 2 right here. If you switch the order and you put cosine in the first column, you will get positive 3e to the negative 2x. And you can also verify that if you substitute these two functions into the original equation by taking your two derivatives, that they will, in fact, the algebra is quite nasty, but they will, in fact, satisfy the differential equation.